Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It is wonderful to be back with you.
Today, we are exploring the ultimate fate of the universe.
Which, honestly, it feels a little heavy for a Tuesday, doesn't it?
A little, yeah. I mean, usually we're digging into, economic models or historical events.
Right, supply chains or the history of coffee or something.
Also-
But today we are talking about the absolute end of, well, everything.
The whole enchilada.
Yeah.
The beginning, the middle, and the inevitable curtain call for reality itself. And I had to admit, when I looked at the research pile for this, I had a bit of an existential crisis.
Oh, I'm sure it's hard not to.
I was reading this stuff at 11 p.m. and then just, staring at my ceiling thinking, does my mortgage really matter if the universe is going to rip itself apart?
That is a very, very valid question. And I think that's why cosmology captures people's imaginations. It forces you to zoom out way, way out until your problems start to look very, very small.
Right. But here's the thing. For a long time, we thought we knew the answer. We thought the story of the universe was a closed book.
I remember this from school. I remember watching those documentaries in the early 2000s, and the narrative was pretty clear. The universe started with the Big Bang, it's expanding, and it's just going to keep expanding forever.
Yep.
It gets colder, darker, and eventually the lights go out. A very slow, kind of boring death. Case closed.
That was the consensus? Absolutely. We called it the big freeze or heat death. It was scientifically consistent with everything we knew at the time. But, and this is why we are having this conversation today, that case has been reopened.
And not just reopened, it feels like it's been blown wide open. We're looking at these massive new data sets released in 2024 and 2025, specifically from this incredible machine called DSI, the Dark Energy Spectroscopic Instrument.
An absolute marvel of engineering.
And this data is telling us that our standard understanding of the universe, it might be wrong.
Wrong might be too gentle a word. The standard model, our sort of recipe for the universe, is cracking at the seams. We're seeing these things that cosmologists call tensions in the data.
The numbers just aren't adding up.
They're not. And because of that, the ending of the movie is, well, it's up for grabs again.
So our mission today is to figure out what's going on. We need to unpack that standard model, look at these cracks that are forming, and then explore the new scenarios for the end of the world. And I have to warn you, if you're listening, some of these are terrifying and some are just weirdly beautiful.
We've got the big freeze, the big crunch, the big rip.
And the big slurp. I still can't believe that's a real scientific term.
Physicists are not known for their, let's say, poetic naming conventions, but the concept behind it is genuinely terrifying.
Okay, let's do this. Let's start with part one, foundations. What do we think we know? Because before we break the universe, we have to establish the baseline. You mentioned the standard model of cosmology. What is that exactly?
Okay, so think of the standard model as the ultimate recipe. If you wanted to bake a universe from scratch that looks exactly like ours, this is the list of ingredients you would need.
The cosmic cookbook.
Precisely. In the scientific community, we call it ΛCDM.
ΛCDM sounds like a piece of lab equipment or, a secret society.
It does have that vibe, but it's actually an acronym for the main ingredients. The lambda symbol, the Greek letter, represents dark energy, and CDM stands for cold dark matter.
Okay, so let's bake a universe. What are the proportions? This is where it gets weird.
Okay, this is usually the first shock for people. If you take the entire energy budget of the universe, everything that exists, all the stuff you and I are made of, atoms, stars, gas, trees, these microphones, our coffee.
Everything we've ever seen.
Everything. That's called baryonic matter, and it makes up about 5% of the universe.
5%. That can't be right.
That's it, 5%.
So literally everything we have ever seen, touched, or, loved.
Yeah.
Every star in the night sky is just the sprinkles on the cake.
Exactly. We are the sprinkles. We are the decorative foam on the vast, dark ocean. The overwhelming majority of the universe is the dark sector. About 25% is something called cold dark matter.
Okay, let's distinguish these two because I feel like people mix them up all the time. Dark matter versus dark energy. Dark matter is the glue, right? It pulls things together.
That's a great way to put it. Think of cold dark matter as the invisible scaffolding of the cosmos. It has mass, so it has gravity. It's the silent architect that pulls things together. We can't see it. It doesn't interact with light. It doesn't emit radiation. But we know it's there because of how galaxies behave.
How so? What's the smoking gun for dark matter?
The biggest one is galaxy rotation curves. Look at a galaxy like our own Milky Way. It's spinning. Based on all the visible stars and gas we can see, the 5% sprinkles, there isn't nearly enough gravity to hold it together.
It's moving too fast.
Way too fast. It's spinning so quickly that it should have flung itself apart billions of years ago, like a wet dog shaking off water. But it doesn't. Something invisible, some huge amount of extra mass is providing the gravitational glue to hold it together.
And that's dark matter.
That's dark matter. It forms these huge invisible halos that galaxies live inside of.
Okay, so 5% sprinkles, 25% invisible glue. That leaves about 70%.
The remaining 68 to 70% is dark energy. That's the lambda.
And if dark matter is the glue, dark energy is the opposite, the thing pushing it all apart. The yeast in your cake analogy.
Yes, the yeast, or the wind in the sails. It's the mysterious force that makes the universe expand. But unlike gravity, which is attractive, dark energy is repulsive. It pushes space itself apart.
And this is the key part of the standard model,
Yeah.
right? For the last, 25 years, we assumed this dark energy was a cosmological constant.
Correct. This was an old idea of Einstein's, actually. He put it into his equations to keep the universe static because he thought it wasn't expanding.
His biggest blunder.
He called it that, yes. When Hubble discovered the universe was expanding, Einstein threw the constant away. But then, in 1998, when we discovered the expansion was accelerating, we had to bring it back.
To explain the acceleration.
Exactly. The idea of a cosmological constant is that dark energy is an intrinsic property of space itself. If you have a cubic meter of empty space, it has a set amount of this energy pushing outward. It's the energy of the vacuum.
Okay, so it's not stuff in space, it's a property of space.
That's the crucial distinction. Now, imagine the universe expands. You now have more space. Since the energy is a property of this space, you now have more energy. But the density, the amount of push per cubic meter, stays exactly the same.
It's constant.
It's constant. It doesn't dilute as the universe expands like normal matter does. It doesn't get tired.
So if I have a box, and I stretch that box of space to be double the size, I now have double the total amount of push.
Precisely. And that's why the expansion accelerates. More space equals more push, which creates more space, which creates more push. It's a runaway feedback loop.
Got it. Okay, so that's the recipe for the cake. But the notes also talk about the baking pan, the geometry of the universe. This always trips me up. How can the universe have a shape if it's everything?
It's a genuinely mind-bending concept. We're not talking about the shape of the cloud of galaxies like a sphere or a blob. We're talking about the shape of the grid paper that the galaxies are drawn on, the intrinsic geometry of space-time itself.
And the options are flat, closed, or open.
Those are the three main possibilities, yes.
Now, when you say flat, you don't mean like a pancake, right? Because I can look up and down and left and right. The world is definitely 3D.
No, not flat like a pancake. We mean Euclidean. Remember high school geometry?
Vaguely.
Yeah.
I try to suppress most of those memories.
Well, do you remember the rule about triangles? If you draw a triangle on a flat piece of paper, the three angles inside will always add up to 180 degrees.
Right. 60, 60, 60. Or 90, 45, 45. That
Yeah.
I remember.
Exactly. That rule only works on a flat surface. If you try to draw a giant triangle on the surface of a basketball, let's say from the North Pole down to the equator over a quarter of the way and then back up.
The lines are curved.
The lines are curved, and the angles will add up to more than 180 degrees. That's a closed or spherical geometry.
And open.
Open is a saddle shape, or maybe a Pringles chip. It curves in two different directions. In that universe, the angles of a triangle would add up to less than 180 degrees. Parallel lines would eventually just peel away from each other.
So which one is our universe? What's the verdict on the cosmic Pringle?
For a long time, the data from our best telescopes, satellites like WMAP and especially Planck, which measured the early universe, has told us that the universe is flat.
Just flat.
And I mean shockingly flat, to within a 0.4% margin of error. As far as we can tell, it's perfectly Euclidean.
That seems like a really weird coincidence. Of all the possible shapes, why would it be perfectly flat?
That is a fantastic question, and it's one that bothered physicists for a very long time. It's called the flatness problem. The solution they came up with is a theory called cosmic inflation.
Allen Guth, 1980.
That's the one. The idea is that in the tiniest, most infinitesimal fraction of a second after the Big Bang, we're talking 10 to the negative 36 seconds, a timescale that is just impossible to comprehend.
So basically instantly.
Instantly. The universe didn't just expand, it inflated. It ballooned outward at a rate that's faster than the speed of light.
How much did it grow? Can we even put a number on that?
The common estimate is that it expanded by a factor of at least 10 to the power of 26.
My brain just short-circuited trying to picture that number.
Okay, let's use an analogy.
Oh.
Imagine you have a tiny, wrinkled, shriveled balloon. That represents the early, chaotic, curved universe. Now imagine blowing that balloon up until it is the size of the entire observable universe today.
Okay, a very, very big balloon.
Now, imagine you are a tiny ant standing on the surface of that balloon. Because it has been stretched so incredibly far, so incredibly tight, as far as you can see in any direction, the ground looks perfectly flat.
The curve is still there, but it's on a scale so huge I could never measure it.
Precisely. Inflation took whatever initial curves or wrinkles existed in space-time and stretched them out until they effectively disappeared from our view.
So because of inflation, we live in a flat universe. And because of the standard model, we have constant dark energy. And if you put those two fundamental assumptions together,
You get the big freeze. If the universe is flat and dark energy never changes, there's nothing to stop the expansion. It just keeps going. The galaxies move apart faster and faster.
and eventually they start moving away from us faster than the speed of light.
Correct. Which means the light from them can never reach us again. They vanish from our view, one by one, over the cosmic horizon.
That is an incredibly spooky thought. Future astronomers, billions of years from now, looking up and seeing nothing.
Exactly. They would look up with their telescopes and see only the stars in our own local group of galaxies, which are gravitationally bound together. They would think the entire universe was just us, surrounded by an endless, eternal dark.
They'd have no evidence of the Big Bang.
None whatsoever. And then, over trillions of years, the stars themselves burn out. The gas to form new stars is used up. Black holes slowly evaporate through Hawking radiation. The temperature of the universe drops closer and closer to absolute zero.
It's a lonely, cold, quiet ending.
It's the ultimate heat death. Maximum entropy, a cold, dark, empty expanse where time itself becomes almost meaningless.
Well, that's thoroughly depressing. But as you said earlier, that was the case closed scenario. That's what we thought was happening for a long time.
That was the consensus until we started measuring things a little more carefully.
And this brings us to section 2, active debate, the tensions, which is a very polite scientific word for we have a major, major problem.
It is a very polite word for what's becoming a very big fight in cosmology. As our technology got better and our measurements became more precise, we started getting different answers to the same fundamental questions.
The biggest one, the one that really makes the headlines, is the Hubble tension.
The H-naught tension, yes. This is the crisis of the expansion rate.
Okay, break this down for us. We're trying to measure how fast the universe is expanding right now, correct?
Correct. We want to find a single number, the Hubble constant, which we measure in kilometers per second per megaparsec.
Hold on, let's pause on megaparsec. That sounds like something Han Solo would say to impress people. I made the Kessel run in less than 12 parsecs. Can we ground that term for a second?
Fair point. A parsec is just a unit of distance astronomers use. It's about 3.26 light years. A megaparsec is simply a million parsecs. So roughly 3.26 million light years. It's just a convenient yardstick for cosmic distances. So when we say the expansion rate is, for example, 70 kilometers per second per megaparsec, what we mean is that for every megaparsec you look out into space, the galaxies are moving away from us 70 kilometers per second faster.
Got it. So galaxy 2 megaparsecs away is receding at 140 kilometers per second.
Exactly. The further out you look, the faster they go. Now here's the problem. We have two main independent ways to measure this number. I like to call them Team Early Universe and Team Late Universe.
Okay, so Team Early Universe, they use the baby picture of the cosmos.
Yes, they look at the cosmic microwave background, the CMB. They use the incredibly precise data from the Planck satellite. This is light from when the universe was only 380,000 years old.
It's basically a fossil.
It's the oldest light in the universe. We can measure the physics of that baby universe, the size of the hot and cold spots in the CMB, with stunning precision. Then we take our standard model recipe, the ΛCDM model, and we run the math forward 13.8 billion years.
And you're making a prediction.
We're making a prediction. It's like looking at a baby's growth chart and saying, based on your height and weight at 6 months old and our standard model of human growth, you should be 6'2" when you're 25.
A perfectly reasonable thing to do. So what does the prediction say?
When Team Early Universe does this, the math consistently says the answer should be about 67 kilometers per second per megaparsec. Give or take a little.
Okay, 67. That's the prediction. Now, what does Team Late Universe say?
Team Late Universe, led by groups like the SH0ES team, doesn't predict. They measure directly. They look at the universe now.
They're measuring the actual 25-year-old adult.
Exactly. They use what we call the cosmic distance ladder. They start with stars in our own galaxy called Cepheid variables.
What are those?
They're a special kind of star that pulsates, getting brighter and dimmer over a regular period. And Henrietta Leavitt discovered over a century ago that the speed of their pulse is directly related to their true brightness.
So if you measure how fast they blink, you know how bright they really are.
Precisely. And if you know how bright something truly is and you see how dim it appears, you can calculate its distance.
Like knowing a 100-watt bulb is always 100 watts. If it looks dim, it's far away.
Perfect analogy. So we use Cepheids to measure the distance to nearby galaxies. Then, in those same galaxies, we look for a specific type of exploding star A, type 1a supernova.
The standard
Yeah,
candle.
the ultimate standard candles. They all explode with almost the exact same peak brightness. So once we calibrate them with the Cepheids, we can spot these supernovae in very, very distant galaxies and measure their distances.
So you're building a ladder of measurements further and further out.
Step by step. And when you do all of that and measure how fast those distant galaxies are moving away from us right now, you get a number. And the number is 73 kilometers per second per megaparsec.
73.
73.
So 67 versus 73. Now, to the average person, that sounds like it could be a rounding error. Who cares about a difference of 6? Why is this a crisis in capital letters?
Because in precision cosmology, with the error bars we have now, that isn't a crack. That's a chasm. This is a 5 sigma discrepancy.
We hear the term sigma thrown around a lot in science news. What does 5 sigma actually mean in terms of probability?
Sigma is a measure of standard deviation. It tells you how likely it is that your result is just a random statistical fluke. 1 sigma is pretty common. 2 is interesting. 3 sigma is considered evidence. But 5 sigma,
That's the gold standard.
that is the gold standard for a discovery in particle physics. It was the standard used for the Higgs boson. 5 sigma means the chance of this difference being just bad luck, a statistical accident, is about 1 in 3.5 million.
So it's not an accident.
It is almost certainly not an accident. The measurements are robust, the teams are brilliant, they've checked their work for years, which means one of 2 things must be true. Either our measurements are wrong in some subtle, systematic way that nobody can figure out.
Or the growth chart is wrong. The standard model is broken.
Exactly. Our understanding of the universe's history is wrong. The baby is growing faster than the growth chart says it should. We are missing something fundamental in the physics.
And that's just the first crack. You mentioned another one, the S8 tension.
Yes. The clumpiness tension?
What?
The clumpiness, S8 is a parameter that measures how much matter clusters together. You know, how lumpy the universe is.
Okay.
The standard model, the ΛCDM model, predicts that gravity should have pulled matter into pretty dense clumps by now. It should be a certain level of lumpy. But when we look at the actual universe using a technique called weak gravitational lensing,
Which is measuring how the gravity of all that matter, including dark matter, bends the light from distant galaxies.
correct. You look at the shapes of billions of background galaxies and see how they're subtly distorted by the matter in front of them. It lets you map the invisible dark matter. And when we do that, we see that the universe is actually smoother than predicted.
So it's less clumpy.
It's about 10% less clumpy than the model says it should be. The significance for this one is lower, maybe 2 to 3 sigma, so it's not a crisis on its own. But it's pointing in the same direction as the Hubble tension.
The model is getting it wrong.
The model is over-predicting the amount of structure. So the universe is expanding too fast and it's too smooth. And then there's the third headache.
Oh, there's more?
There's always more. It's called the lensing anomaly. This comes from the Planck data itself, the baby picture. The Planck data shows a little bit more gravitational lensing within its own data than the model would predict.
And what does that imply?
Bizarrely, this extra lensing actually hints that the universe might be closed. Spherical, not flat.
But wait, you just spent 5 minutes convincing me that we know it's flat because of inflation? If we just say, okay, our mistake, it's spherical, doesn't that fix the problem?
You'd think so, but it's a catastrophe. It fixes the lensing anomaly, but it breaks everything else. If you force the cosmological model to be spherical, the Hubble prediction drops from 67 all the way down into the 50s.
It makes the Hubble tension way worse.
You're massively worse. And it completely contradicts other data, like baryon acoustic oscillations, which scream that the universe must be flat. It's a game of cosmological whack-a-mole. You fix one problem and two others pop up somewhere else.
So we are well and truly stuck.
Precisely. We are in a state of confusion. The pieces of the puzzle we have just do not fit in the box anymore.
Which brings us to Section 3. Frontiers. The cavalry is arriving. Or maybe it's the demolition crew. Enter DSII.
The Dark Energy Spectroscopic Instrument. This is the new heavy hitter on the block, an absolute game changer.
Where is this thing located?
It's an instrument mounted on the Mail telescope at Kitt Peak National Observatory in Arizona. And, I mean, the engineering on this thing is something out of science fiction.
I read about the eyes. Tell us about the robotic eyes.
So most telescopes just have a big camera, right? They take a picture of a patch of sky. DSI is different. Its focal plane is packed with 5,000 tiny robotic positioners.
5,000 individual robots.
Little robotic arms, each one holding the tip of a fiber optic cable. In the dark, inside the telescope, these 5,000 robots can independently swivel and point their fiber optic cable at a specific pre-selected galaxy.
And how accurate are they?
They align these cables with an accuracy of less than the width of a human hair.
That is just wild.
And they do this every 20 minutes. The telescope stares at a patch of sky. The 5,000 robots collect the light from 5,000 galaxies for about 20 minutes. Then the telescope moves to a new patch of sky, and in about 2 minutes, all 5,000 robots reconfigure themselves to target 5,000 new galaxies.
It's an assembly line for mapping the universe.
That's exactly what it is. In just its first year of operations, it mapped more galaxies and quasars than all previous 3D surveys in the history of astronomy combined.
What's the final number going to be?
We're talking about a map of over 40 million galaxies and quasars, creating the largest, most detailed 3D map of the universe ever made. It allows us to look back in time over 11 billion years.
And the main tool they're using to do this, to measure the expansion, is something called BAO, Baryon Acoustic Oscillations.
That's the key, yes.
In our pre-show notes, you call these frozen sound waves. That sounds incredibly poetic, but I'm going to need you to break that down for me. How does a sound wave freeze in space?
Okay, visualization time. Let's go back to the baby universe, just after the Big Bang. It wasn't empty space like it is today. It was a hot, dense, opaque soup of plasma, a fog of protons and electrons and photons all bouncing off each other.
A plasma soup, got it.
Now imagine dropping a pebble into a still pond.
Yeah.
You get ripples, right? Concentric circles moving outward.
Yep.
In the early universe, there were tiny density fluctuations, little quantum pebbles that created pressure waves. These were, for all intents and purposes, sound waves. These waves traveled through the plasma soup, moving outward in giant spheres at nearly the speed of light.
Okay, so ripples in the cosmic soup.
But then, at that magical time, 380,000 years after the Big Bang, the universe cooled down enough for protons and electrons to combine and form neutral hydrogen atoms. The fog cleared, the soup disappeared and became transparent gas.
And the sound waves.
Suddenly, the sound waves couldn't travel anymore. The medium they were moving through vanished. They stopped dead in their tracks. They froze.
Ah, I see.
And the matter that was riding on the crest of those waves, the slightly denser part, it got stranded there. So what you were left with was a slight overdensity of matter in a shell at a specific distance from the center of the original disturbance.
So fast forward 13 billion years. What does that look like today?
It means that if you pick any galaxy, there is a slightly higher probability of finding another galaxy at a specific distance from it. It's a very faint statistical preference, a ghost of that sound wave. It's about 500 million light years across today.
So nature gave us a ruler, a standard ruler.
Exactly, that's the term we use. Because we know the physics of the plasma soup so well, we know exactly how big that ring should be in physical terms. So if we look out into the universe and measure how big those rings appear to be in the sky, we can tell exactly how far away they are.
It's basic trigonometry on a cosmic scale. If I know a car is 6 feet tall and I see how small it looks in a photo, I can tell you how far away the photo was taken from.
That's the perfect analogy. And by doing this for millions of galaxies at different distances, which means looking back to different times, we can create an ultra-precise history of how fast the universe was expanding at different points in its life.
So DSI did this. They mapped millions of these frozen ripples. And in 2024 and 2025, they dropped their first major results. And this is the plot twist of our story. What did they find?
This is where the floor drops out from under the standard model.
Yep.
When they combined the DSI data with all the other major data sets, the CMB from Planck, the supernovae data, they found something that just shouldn't be there. They found strong evidence that dark energy does not look like a constant.
It's changing.
It seems to be evolving over cosmic time.
Evolving how? Is it getting stronger, weaker? What's the trend?
The data, with a few different analysis methods, suggests that dark energy is weakening.
Whoa. So the push that's accelerating the expansion is running out of gas.
That is what the data appears to be telling us. In our equations, we use a parameter called the equation of state parameter. If dark energy is the standard model cosmological constant, WE should be equal to -1. Exactly -1. Forever. Unchanging.
And DSI says,
DSI's data hints that W is not -1, it's drifting. The statistical significance is somewhere between 2.6 and 3.9 sigma, depending on which data sets you combine and how you slice the analysis.
okay, so again, not quite the 5 sigma gold standard yet, but way, way too high to be a fluke. It's something you have to take very seriously.
It is the strongest evidence we have ever had that the cosmological constant is wrong. It suggests we might live in a universe with dynamical dark energy. The energy of the vacuum is not fixed, it's fluid. It changes.
There was a mention in the research of a new theory called the dead universe theory. Is that related to this?
Yes. When this Crises A data started pointing towards evolving dark energy, theorists started scrambling to find a model that fits all the pieces together. The dead universe theory is one of the new proposals. It suggests that the expansion is undergoing a kind of thermodynamic retraction.
And the crazy thing I read is that this one theory solves multiple problems at once.
It's remarkable. In its initial form, this model seems to resolve the Hubble tension and the S8 tension simultaneously. It predicts that the universe should be expanding faster now and should be smoother than ΛCDM predicts.
So if you assume dark energy is dying, all the weird tensions in the data suddenly make sense. The math just works.
It works disturbingly well. Now, it's a new theory, it needs a lot more testing, but it's a powerful sign that we're on the right track with this idea of evolving dark energy.
This changes everything. I mean, fundamentally. If dark energy is weakening, then the cosmic tug-of-war between expansion, the push, and gravity, the pull, is shifting. The balance of power is changing. Gravity might actually have a chance to win in the long run.
Exactly. And that leads us directly to the end of the world, or rather the possible ends of the world.
Section 4. Implications. The fate of the universe.
Yeah.
Because if the standard model is on its deathbed, then the boring old big freeze isn't the only option on the menu anymore.
We have to reopen the menu. And frankly, the other options are a lot more dramatic.
Let's walk through them one by one. Scenario 1 is still the big freeze, right? That one isn't completely off the table.
No, it is still very possible. It's important to remember that. Even if dark energy is weakening, as long as it stays positive and doesn't disappear entirely, the universe will continue to expand. It might just expand slower than we thought.
So we can still get the heat death ending.
Yes, it might just settle down to a new, lower energy constant, in which case we're back to the whimper ending. Lonely, cold, dark.
But now, thanks to DEGI, Scenario 2 is making a huge comeback. The comeback kid, you called it. The big crunch.
This is the one that feels like a classic sci-fi movie. It was the leading theory for a long time, before dark energy was discovered.
So paint the picture for us. If dark energy weakens enough, if it goes to zero or even becomes negative, what happens?
Imagine you throw a ball straight up into the air. That's the Big Bang. The ball goes up, fighting gravity, that's the expansion. Dark energy in the old model was like a rocket booster strapped to the ball that kept it going up forever and ever, faster and faster.
But now the rocket might be running out of fuel.
Exactly. If the rocket runs out of fuel, gravity is still there, patiently pulling. The ball slows down, it reaches a peak height, stops for an infinitesimal moment, and then it starts to fall back down.
So the expansion of the universe grinds to a halt. It stops.
It would stop. For a moment, cosmic time would seem to stand still, and then the contraction would begin.
And we would see this, right, in our telescopes. Instead of seeing galaxies redshifted, their light stretched out as they move away, we would start to see blue shift.
We would. Astronomers would look up and see the nearest galaxies rushing toward us. Their light would be compressed, shifted to the blue end of the spectrum. Then the further ones would slow down, stop, and start coming back too. The universe would start getting smaller.
And as it gets smaller, it gets hotter.
Much, much hotter. Remember the cosmic microwave background? That leftover radiation from the Big Bang that's currently super cold, just 2.7 degrees above absolute zero?
Yeah.
As you shrink the universe, you compress that radiation, just like compressing gas in a piston heats it up. The background temperature of empty space itself would start to rise.
From freezing to what?
First to a comfortable room temperature, then to the heat of an oven, then to the searing heat of a furnace.
So space itself becomes an oven cooking everything in it.
Eventually, the background sky would become hotter than the surface of the stars. Stars wouldn't be able to radiate away their heat. They would begin to boil from the outside in.
That is a genuinely horrific image. Stars boiling.
And in the final moments, matter itself gets crushed. Galaxies merge in a chaotic mess. Stars collide. Eventually, the temperature and pressure become so immense that atoms are smashed apart into their constituent particles. Everything returns to a hot, dense singularity.
The ultimate trash compactor. But wait, there's a variation on this, isn't there? A possible silver lining. The big bounce.
There's a theory, especially in fields like loop quantum gravity, that suggests the Big Crunch doesn't just end in an infinite, unknowable singularity. The idea is that as you compress space-time, quantum gravity effects take over and cause it to bounce.
So the crunch triggers a new Big Bang.
A new Big Bang, a cyclic universe.
Expansion, contraction, bounce. Expansion, contraction, bounce. Forever.
A cosmic heartbeat. Death and rebirth on a scale we can't imagine.
You know, I find that oddly comforting. It feels less final. It means we aren't just a one-off accident. We're just one chapter in an eternal story.
It has a certain philosophical elegance, doesn't it?
It really does. Okay, let's ruin that vibe completely. Scenario 3, the Big Rib.
The nightmare scenario.
This happens if the DSI data is right, that dark energy is changing. But maybe we're wrong about the direction. What if, instead of weakening, it gets stronger over time?
This is a hypothetical form of energy called phantom energy. In this case, the equation of state parameter, W, drops to a value less than -1. If that happens, the dark energy density actually increases as the universe expands.
So the more space you have, the more powerful the repulsive push gets. It's a runaway train with no brakes.
It's worse than that. It's a runaway train that's building its own engine as it goes. The acceleration doesn't just continue, it accelerates. It goes to infinity.
Walk us through the timeline of the rip. How does this play out?
Okay. At first, it's not so bad. The expansion just gets so fast that it starts to overcome the gravity holding clusters of galaxies together. The Virgo supercluster dissolves. The Milky Way becomes an isolated island galaxy.
But then it gets closer to home.
Then, in the final stages, the phantom energy's repulsive force becomes stronger than the gravity of our own galaxy. The Milky Way is torn apart, the stars are all flung away from each other into the dark.
And then the solar system.
Yes. About 3 months before the final end, the expansion becomes strong enough to rip the Earth away from the sun's gravity. The planets all spiral out into the cold.
And then the Earth itself.
In the last 30 minutes, the expansion force becomes stronger than the Earth's own gravity. The planet disintegrates. In the last few minutes, it's stronger than the electromagnetic forces holding rocks and buildings together. Mountains crumble into dust.
And then us. Atoms.
In the final fraction of a second, the expansion of space itself becomes so violent that it rips electrons away from their atomic nuclei. And in the very, very last instant, it becomes stronger than the strong nuclear force. And it rips the quarks out of protons and neutrons. The fabric of space-time itself is shredded.
That is thorough.
It is the most complete and violent ending imaginable.
And finally, scenario 4. The wild card. The Big Slurp. Which sounds like a drink from a convenience store, but is actually a synonym for instant, universe-wide death.
This one is tricky because it doesn't necessarily depend on dark energy. It depends on the stability of the Higgs field.
A Higgs boson. The God particle that gives everything mass.
Exactly. The Higgs field pervades all of space. We assume the field is in its lowest possible energy state. It's stable. Imagine a ball sitting at the very bottom of a deep valley. It's happy there. It's not going anywhere. But the math suggests we might not be in the deepest valley. We might be in a false vacuum. Imagine the ball is in a little dip on the side of a mountain, but there is a much, much deeper valley right next to it, separated by a hill.
It's stable for now, but not truly stable.
It's metastable. And in quantum mechanics, particles can tunnel through barriers. A random quantum fluctuation or a very high-energy event could theoretically push the Higgs field ball over that hill. If that happened, it would crash down to the true lower energy state.
And what happens to our part of the universe when the Higgs field changes its value?
A bubble of true vacuum would form at that point. Inside that bubble, the fundamental laws of physics would be completely different. The value of the Higgs field would be different, so the masses of all fundamental particles would change. Chemistry, as we know it, would be impossible. Atoms couldn't hold together.
And this bubble, it expands.
It would expand outward in all directions at the speed of light.
So, we would never see it coming.
You couldn't. By definition, since the wall of the bubble moves at the speed of light, no information about it can reach you before it arrives. One moment you're sitting here listening to this, and the next nanosecond you are just deleted. The laws of physics that hold your atoms together just switch off.
That is, uh, honestly, of the three violent endings, that's the one I'd choose. Just lights out, no bowling stars, no being ripped apart atom by atom, just efficient deletion.
It is certain. For the last century, science has been moving toward this idea of Occam's razor, that the simplest explanation is probably the best one. We wanted a simple, elegant, constant, flat universe. But the psi data, the tensions, the complexity, it's telling us that the universe has no obligation to be simple for us.
It's messy. It's complicated.
It is beautifully and wonderfully messy, and it also highlights what's known as the coincidence problem.
The why now question.
Exactly. Why do we happen to live in the specific era of the universe when the density of matter and the density of dark energy are roughly comparable? If we lived in the distant past, matter would have been completely dominant. If we live in the far future, dark energy will be. We live in this bizarrely specific window of time, the Goldilocks era.
We were late enough to the party that stars and galaxies and life have had time to form.
But we're early enough that we can still see the rest of the universe. If we lived 1 trillion years in the future, in the Big Freeze scenario, the expansion would have pushed every other galaxy beyond our cosmic horizon. We would look up and think we were utterly alone.
We wouldn't know about the Big Bang. We'd have no clue about the expansion of the universe.
We would be cosmically ignorant, trapped in our own little island. We are the witnesses. We might be living in the only era in the universe's long history when intelligent beings can actually piece together the whole story.
That actually gives me chills.
Yeah.
The idea that we are the universe's way of understanding itself, and we just happen to wake up at the exact moment where all the crucial clues are still visible before they fade away forever.
Exactly. It's an incredible privilege.
That is a profound thought. It makes the whole crisis in cosmology feel less like a failure of our models and more like an incredible opportunity.
It is, without a doubt, the most exciting time to be a cosmologist in history. In 1900, Lord Kelvin famously said there was nothing new in physics left to be discovered.
He was a little off.
Just a bit. In
Right.
1990, we thought cosmology was mostly solved. In 2026, we are realizing we're just getting started. The universe is far stranger and more mysterious than we ever imagined.
The book is enclosed. We're maybe
Yeah.
on chapter 2.
I'd say we're still writing the prologue.
I love that. The search continues.
Always.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.